Hello all. Here I am today to explain the experiment on frequency shifting modulator and demodulator. So before starting it, actually the experiment, we'll see what the block schematics over here are, and then we'll start with the experimental setup. So you can see that there are two ICs which are used. One IC is XR2206 and the other IC is XR2211. So XR2206 actually XR stands for transmitter and receiver. So it's a transceiver IC which has been used, but there is a switch which has been used inside the XR2206 where there is a switching between the two frequency components. How the switching is there? There is an RC circuit which has been connected. So if it's logical 1, then it is going to select one frequency. If it is logic 0, then it is going to select other frequency. So the frequencies which are selected will be as per the data pattern which has been connected. As we are aware that Fsk modulator is a digital modulation technique, and hence the data is going to be a digital data which is going to be in the form of 1 and 0. So here we'll start with first what is the data pattern, the modulated output, and we'll see the demodulated output at the end of the receiver. So here we have XR2211, which is nothing but again a transceiver IC, but here it acts as a PLL function, and we are using it as a PLL. So here that is a transceiver IC which is used as the transmitter, that is a 2206, and the receiver that is 2211, but it acts as a PLL function. So starting with the pattern which has been generated over here, so we'll see what the pattern is. What I have connected is, I have connected the CRO ground to one of the terminal, that is the ground terminal provided on the kit, and this is the point where the patterns are being generated. There are two patterns which are generated. I'll just show the one pattern. So I have connected the positive terminal of the CRO probe to one of the pattern. So we'll see now on the CRO what the pattern is going to look like. So I'll just show you the pattern on the CRO. We'll just check what the pattern is. So here, this is the pattern which has been generated. Now what the pattern says is, see, the pattern is 1, then it is 1, 2 and 3 zeros, again a 1 and 1, 2 and 3 zeros. So if you can find out here, you can see that the pattern is again 1 0 0 0 0 1 0 0 0 1. So it is a repeated pattern which has been there. Now I'll show you the second pattern. I'm connecting the second pattern over here. So this is the second pattern which is there. What is the second pattern? We'll read the second pattern. It is 1, then it is a 0, then again it is a 1, and it is 2 times 0. So you can see the same pattern which has been repeated, 1 0 1 and a 00 which has been repeated, right? So what we'll do is, now we'll connect this pattern as an input to this particular modulator, correct? So what I'm doing is, I'm connecting the pattern as an input to the modulator. So I'm using the pattern that is second pattern. Why? Because it is showing me more variation. What variations? That is, it is having 1 0 1 00. So there are more variations, so we can see the Fsk variations at the output of the modulator, right? So this is given as a point which is given as an input over here. So I'll be connecting the pattern generator input as an input to the modulator, correct? So this is the input to the modulator. Now we'll check the Fsk, that is the output, modulated output which has been there. So this is a point where Fsk output can be checked by. Now I'll be looking the Fsk output with respect to the pattern input. So first what I'll do is, I'll connect instead the channel 1 as an input to the pattern, and will connect the channel 2 as an input to the that is a Fsk output. So I am connecting the pattern, that is the second input CRO probe as an input to whom, that is the Fsk output. Now we'll see what is the Fsk output which is looks like here. So I'll just show you what is the Fsk output. Just a minute, I'm just adjusting the frequency component over here so that the output will match. Okay, right. So with this, let me see the match code. Okay, I have changed the pattern. I have made the pattern as 1 1 00 1 and 4 times 0 the pattern, because we'll just see later what the issue is, but here I can see that there is a frequency variation which you can observe between the two, that is 1 and 0. So you can see that there is one frequency component which is seen, that is a high frequency component corresponding to logic 1, and a low frequency component corresponding to logic 0. So you can see a high frequency component logic 1 and low frequency component that is corresponding to logic 0. Now this is your Fsk output, that is giving you one frequency for logic 1, the other frequency for logic 0, correct? So now what I want is, I want to measure this frequency component. This I'll call it as one F1 frequency, and this I'll call it as an F2 frequency. So the carrier frequency which is selected in Fsk is F1 plus F2 divided by 2. That is how we select the carrier frequency. Now to measure this F1 and F2 so that I can decide the carrier frequency, I need to measure it, or rather to recover the Fsk demodulated signal, we need this difference frequency to be minimum. That is the difference between F1 and F2 to be minimum, so that it can be recovered very easily at the receiver end, correct? So I'll show you now how to measure this F1 and F2. Now see, we can see that it is not a stable waveform which you can observe it on the CRO. You can make the waveform stable, but still it's difficult to measure the frequency component on the CRO, and hence there is a way where you can say that if I connect instead of 1-0 pattern, if I connect, that is I give as an input a logic 1, that is all the input as logic 1, I'll get F1 frequency, and if I give logic 0 as an input, I'll get it as F2 frequency. So how to do this? We have a provision that is being given on a kit. Instead of giving the input through the pattern, now I'll be connecting VCC as an input. Okay, what I'll be connecting is VCC. Means it is nothing but you are giving logic 1 as an input over here, correct? So if I say it is a logic 1, this is what is logic 1 corresponds to. If you want to check whether it is plus 5, I'll just put it to ground, that is the signal to ground, that is a reference. I'll remove the ground connection and just show you that this is the shift in the frequency component, which is, you can say, is equal to 5 volt. So this is corresponding to F1 frequency, correct? And if you connect the same thing, that is the pattern input, to a ground connection over here, you can see correspondingly F2 frequency component. So you can see the frequency is less as compared to when we connect it to that is logic 1 itself, correct? So the frequency is high, you can observe by. So as once again I'll connect it to the pattern input, so you can see that there is a variation in the frequency which we can observe by, correct? So two frequency components, you can see variation in two frequency components, one as the F1 frequency, the other as the F2 frequency. So this is your Fsk output. Now coming to the receiver end, we'll come to the receiver end. Now for the receiver end, it is a PLL which has been used at the receiver. So the PLL block is nothing but you are having the first block, that is a phase comparator, the second block, that is a low pass filter, and the third block is nothing but the VCO. So the VCO initially is oscillating by its frequency, that is we call it as a free running frequency. So you need to adjust this VCO frequency to carrier frequency, and hence what I said is the need of measurement of F1 and F2 frequency component is big there. So we have measured the F1, we have measured the F2 frequencies. Now what we'll do is we'll first adjust the VCO to carrier frequency. So there is a provision which has been given to us, that is to observe the that is VCO over here, and the VCO adjustment is given over here. So the VCO output is fed back as an input to the phase comparator. Input to the phase comparator is either the Fsk F1 frequency or F2 frequency. So comparison between F1 and the carrier will generate logic 1 at the output of the phase comparator, and the low pass filter will that is charge and discharge as per the input which has been there, and this is how the demodulated signal is observed at the output. Now what you have is, you either set the VCO frequency to carrier frequency, or what we can do is we can directly just observe the output of we can say the demodulated output, and adjust the VCO in such a way that you will get the original signal and the detected signal as same. So now what I have shown here is, on the CRO I have connected first at the channel input, that is first channel is nothing but the input which we are giving, that is the data input, and second will be observing as the detected output. Now to get the detected output, you need to connect the modulated output as an input to the detector. So I have connected modulated output as an input to the detector circuit. Okay, then I need to connect this points, that is C and A point, that is connecting the VCO and the phase comparator in feedback which we have connected, and now we are going to together observe the detected output. So you can see the detected output on the CRO, but now what you need is you need to adjust the VCO in such a way that we'll be getting the detected and the transmitted output as same. So I am adjusting the VCO from here, and you will be observing the output that is on the DSO. So I'm adjusting here the VCO in such a way that both the detected and the transmitted are the same. So you can see there is a fine adjustment which has been required for this. So I'm just adjusting so that we get the detected and the transmitted output one and the same. So see, this is somewhere adjusted to, that is the detected and the transmitted, but you can see a shift or a delay in both the circuits, correct? So delay in the recovered circuit is allowed, like we can say that the signal will be received after some delay at the receiver end, but no frequency shift should be there in the that is the detected output. So you need to see that that is the delay can be, that is allowed, but no frequency shift should be there in the received frequency, that is a detected output, right? So this is your detected output. The pattern remains again the same, that is the received pattern remains again the same. So this is about the Fsk modulator and the demodulator. So you can see this is your transmitted output, this is the detected output, that is second channel is nothing but the detected output, the first channel is nothing but the, that is a transmitted output. Now for observations, what we can note down is, we can note down the TB time period of the bit, that is for logic 1 how much is the time period which has been there, and that TB duration and this TB duration can be matched, and we can recover that the transmitted and the received output is same, correct? You can also measure the carrier frequency. We can also that is from F1 and F2 frequency we can measure the carrier frequency. So this is just the connection diagram which we had made. You can also observe the VCO output which has been over here. This VCO output will be connected when we connect the input to this particular B point which has been provided, and you can observe this VCO, which we call it as a free running frequency, on the CRO also, and you can adjust this free running frequency to carrier frequency. As I said, F1 plus F2 divided by 2 will be the free running frequency. So you can either set the VCO to a free running frequency and then check the detected and the transmitted output, or either I said that as I had done it in the reverse way, that is I just checked the detected and the transmitted output and adjusted VCO in such a way that both are same. So this is nothing but adjusting VCO to carrier frequency, correct? So this is all about FSK. Thank you for patiently hearing. If you like it, just like my channel and subscribe it. Thank you.